My name is Vladislav Shpilevoy, and I will tell about SWIM protocol to build a cluster. My talk will follow this plan. First, I will tell about failure detection protocols, then predecessors of gossip protocols. Then I will introduce you SWIM protocol and its algorithm. Afterwards, I will briefly introduce you Tarantul database in which the SWIM was implemented, and I will introduce how exactly it's implemented and with which extensions, which appear to be very important in production systems. After that, I will show some simple usage examples, performance measurement results, and plans for further development of SWIM as a protocol and as a part of Tarantul database. In the beginning, there was a server, a single machine which serves client requests, and everything was okay until it got overwhelmed and many servers were added to help it. And the problem of overload was gone. This is how horizontal scaling was invented. But new challenges appear. There emerged the task of failure detection in clusters, how to detect that a node has failed. And it was needed for eviction of dead nodes, for reparation of broken nodes, and for making centralized decisions in clusters, such as cluster leader change, or replication master failover, or synchronous replication transaction processing. And since 1980s, there has been an incredible growth of articles, researches, protocols, algorithms trying to solve this problem. Starting from simple ones such as let's establish connections between each nodes and just send ping messages, and to such things as attempts to develop a reliable broadcast protocol for sending heartbeat messages. Unfortunately, all such solutions which make links all-to-all scale very poorly. They give quadratical complexity on message count in network, on connection count in network. So it just doesn't work in big clusters. And this is when gossip protocols were invented, also known as infection-style process protocols. They are good in this case because they give at most linear complexity, depending on cluster size. How does it work? Gossip protocols describe efficient detection and dissemination of events in a cluster, and nodes exchange with each other with information they found in the cluster. The exchange is organized like an infection spread. Assume that one node detected an event. For example, it found that some other node has failed. And it will send this event to every other node one by one in random order. Nodes received this event will do the same. They will send it to their random neighbors and so on. So after some time, the whole cluster knows about this event. As we can see, the main difference with failure detection protocols, first difference is that all nodes spread the event, even if just one node found it. They help each other. And gossip algorithms are usually randomized. So we get even load per node almost for free without any synchronization, of course, on average. And every gossip protocol follows this idea one way or another, and differences are in details. First difference is how exactly to detect a failure. Simple way, let nodes just ping each other and expect an ACK message. And if it works, then node is alive. More complex protocols can try indirect pings in case direct ping has failed, because if an ACK message wasn't delivered, it doesn't mean that the recipient of ping was dead. It may mean that this network link was broken, for example. So some protocols can work around this, sending indirect pings. Especially complex protocols can detect own failure of a node. They can find it by sending pings to everyone and seeing that nobody responds, and very likely that this node has failed and not other nodes. For example, it somehow got isolated in its network segment or something. Second difference is how to define failure. Simple protocols just say that there are alive nodes and dead nodes. Node is dead if it doesn't respond or responds too slow. Some protocols may define multiple discrete states, such as SWIM. It defines alive, dead, and suspicious. Especially advanced protocols can define state as a contiguous number for example, on a range from 0 to 1, where 0 means totally available and 0 not available at all. And protocols are free to choose any criteria for moving nodes from one state to another, such as number of not received ACK messages or ping latency or direct or indirect availability and many other criteria. And the last difference is how to disseminate an event after it was found. Simple protocols just do push way. It's when a node which found an event sends it to every other node without asking any permission with every message. Pull protocols is when events are pulled from nodes which learned about this event. For example, a node receives a message saying, give me all the events about some third node, and it sends them. And advanced protocols can combine them in some smart way in order to somehow decrease number of messages in the network. But after all of them give this very, I would say, tasty estimations, which are way better than what failure detections protocols usually give us. First is that if in a cluster any event happens, for example a node failure, at least one other node in this cluster will learn about this event in constant time, not depending on cluster size. After the event is found, it will be fully disseminated to the whole cluster in logarithmic time. So every node will learn about this event. And during work of these protocols, they give at average constant network load per each node and at most linear per the whole cluster. As you can see, gossip protocols are really very attractive for their efficiency in detection and dissemination of events, and especially for being really lightweight, both in understanding and in implementation. And this is why they are really widely used, even though we sometimes don't know about this. For example, Cassandra is a household name in the world of databases. They use their own gossip protocol for monitoring of cluster nodes. Surf is a library using one of SWIM implementations. It's used in is used in console. Scuttlebutt is a protocol, gossip protocol for huge clusters with tens of thousands of nodes. It's oriented on reducing network load. And ScyllaDB, it's some kind of fork from Cassandra, which also uses gossip for cluster nodes monitoring. LifeGuard, it's one another SWIM implementation which aims against false positive failure detections. And there is SWIM, which is now implemented in Tarantul. What is SWIM? It's a scalable, weakly consistent infection-style process group membership protocol. Each part of this name means some important part of SWIM. Scalable means exactly what it says. The protocol is very good at scalability. In constant time, we get failure detections. In logarithmic time, their full dissemination. We have constant even network load per node and linear network load per the whole cluster. Weakly consistent means that this protocol is fully asynchronous. There are no any synchronization or blocking between cluster nodes. It can lead to the case shown on the slide that two nodes can see state of a third node differently for some time if this third node failed recently and this event was not disseminated to the whole cluster yet. But we are guaranteed that after some time, all the nodes will see state of this failed node in the same way. Infection-style process means that it's a typical gossip protocol. Nodes help each other to disseminate events. Group membership means that each node maintains a so-called member table. It's a table where every other known node is stored with its last known state, last known IP and port, and maybe some other attributes at which we will look later. Swim consists of two very independent components. In this sense, it's really similar to Raft, where we have leader election and replication as really two totally independent things. And the Swim as well, we have two totally independent components which can be used, for example, without each other somehow. First is failure detection. It's protocol of how to detect failures, and this is how it works. Each node periodically chooses a random neighbor from those neighbors who wasn't selected for the longest time, for some fairness, and sends a ping message. And in this way, they ping each other, expect ACK messages, and if an ACK wasn't delivered, node is declared suspicious. It's not declared dead right away, and an investigation is started. After suspicion, sender of the original ping will send indirect pings through several randomly selected neighbors, and will expect indirect ACKs. And if at least one indirect ACK is delivered, then probably with this suspicion was just about a temporary network link broken or UDP packet was lost. Swim is based on UDP. And if not any single ACK was received, the node is declared dead. Here, a recipient of these pings was declared first from alive to suspicious, and from suspicious to dead, or back to alive, and all of these are events. They need to be disseminated. Other nodes also should know that this node is suspicious or dead, and this is a job for event dissemination component. It works like follows. All the events are stored into a queue. If there are multiple events for the same node, they are merged into one event, so as not to send outdated information if a newer event rewrites old one. So this queue doesn't grow infinitely. It's limited by number of nodes in the cluster. And when it's time to send the ping message, events are attached to the same packet. It's called piggybacking, when we attach information from several independent components into the same packet. So these components are related only by, are linked only by the transport protocol, and they are not related in any other aspect. Each event is sent logarithmic number of times, and after this it's dropped, because we just can't infinitely send it with UDP, so we can fit infinite number of events here. And logarithm was chosen because it just gives very good probability that each event will be delivered to each node, but I didn't say 100% probability, just very good. We will return to it later. It's one of the Swim problems. How exactly node statuses are updated when events are delivered, and a node unpacks this message and sees that some node is delivered dead, what is declared dead, what should it do? Here is an interesting example showing that it's not really that simple. 3 nodes, B is not available, A node knows this, and C doesn't know this. They exchange this information, who is right. Swim says that in this case, assume the worst. So, okay, they assumed the worst. A and C both think that B is dead. Now B is back alive. How will it restore its state? Because other nodes will assume the worst. B will send them messages, they will ignore them because assume the worst. So Swim needed a way how to refute false gossips, how nodes could clear their name in other member tables, and this is where incarnation concept was introduced. Incarnation is a really simple thing. It's just like logical clock. It's a counter on each node which only this node can increment, and which it attaches to each piece of message sent from this node. And every other node in its member table remembers last known incarnation from each other node. So if a packet with greater incarnation is received than the last known, then we can be sure that this node is actually alive, if we considered it dead before. In this concrete case, B after some time we'll learn that other nodes think that it's dead. This may happen because B connected back to the cluster, or A and C still send messages to B, hoping that it will resurrect sometime. So after all, B found that other nodes think it's dead. B increments its incarnation, sends it back to other nodes. They update B state back to alive, and they will help B to disseminate this information, because incarnation update is also an event. So B name is cleared, and it's again alive. And the rule becomes this: assume the worst, but greater incarnation means newer information. And since Swim uses UDP, it faces UDP problems such as packet duplicates, late delivery of packets, packet losses, and incarnation helps to protect us from one of these problems, late delivery, because if a very old packet somehow got delivered and it contains outdated information, it will contain outdated incarnation as well, and it just will be discarded. Not the whole packet, just events which are considered discarded. And other problems of UDP just doesn't matter for Swim. It's okay to duplicate a packet or to lose it because they are resent anyway. Before we can get to Swim API and implementation and extensions, we need to understand something about Tarantul. What is it? So you just need to know how it works to understand what will happen later. Tarantul is a common purpose database and application server working together on board, right, in one process, in one address space. So you can write your application logic right close to database without wasting time on going to by network to a remote database node or something. It's written in pure C, sometimes in somewhere in C++, but offers interfaces on SQL, Lua, and C. Lua is the main language used in our application server on which application logic is usually written. But you can write it in pure C, of course. We offer two engines: in memory engine and on disk engine. In memory has 3 hash R3 indexes. On disk engine has LSM trees, like in my rocks in MySQL. In memory engine is persistent. Data is persisted in write-ahead log, so after restart it's recovered and your data is not lost. You can write stored procedures, so any of these 3 languages used for application server. And here is an architecture of Tarantul. It consists of 3 main threads. First thread is network. Its task is reading, writing to client sockets, packing and packing data, batching of requests, and so on. Wall thread, it's write-ahead log thread. Its only task is writing write-ahead logs, tens and hundreds of thousands of them each second, and it's heavily optimized for better memory management, for avoiding frequency calls. And one main thread for all the logic, all the application logic for working with the database, creation of tables, indexes, accessing them, whatever. And this thread is able solely serve multiple requests simultaneously. How does it work? It works because the thread implements cooperative multitasking. As we know, there is preemptive multitasking used in Linux kernel when processes are interrupted without being asked for this, and cooperative multitasking when you are able to choose when you want to switch to a next task. So here it works like follows. This thread has tens and hundreds of thousands of fibers, so-called. Fiber is just looks from user point of view, it looks like a thread. It has its own stack, and it's implemented in user space, and users can switch from one fiber to next fiber to execute them in this thread. And it's scheduled in user space by user. And this is how typically it works. A user request arrives to our database. It's assigned to a fiber. Fiber starts writing some transaction. It calls commit. Commit goes to write-ahead log thread, and while write-ahead log writes this on disk, main thread is switched to the next fiber, and it doesn't waste time on waiting, on mutexes locking or whatever. So with this architecture, Tarantul fully utilizes all the CPU cores on which it works, not needed job. And here is a couple of short examples which we are going to need to understand Swim examples. First is configuration of Tarantul on Lua language. I call function box CFG. I pass it IP port on which Tarantul should listen for client connections, and that it will be a part of replication set consisting of 2 nodes, this and some other node. Then the second example, how to connect to a remote Tarantul using built-in netbox module. Here I call require, it's like import in Python. I import netbox module, I connect to some remote Tarantul, send ping message, call some stored function, and so on. So now we are ready to look at Swim interface. Swim is implemented also in pure C and provides Lua interface, so you could use it in application server. It's simple to import it, just call require Swim and it's ready to use. You can create, after importing Swim, you can create multiple Swim nodes inside one process in case your Tarantul is a part of several clusters at once. It happens sometimes in production. After creation, you can configure it. Almost anything what I said about Swim can be configured, starting from heartbeat rate. It's how often this node should send pings to random neighbors. Again, I should say it's not purely random because we send pings only to nodes which for the longest time weren't sent a ping message, so to achieve some fairness. Egg timeout is when a ping message is considered unacknowledged. URI, IP port, EUID, it's a very interesting moment. The original Swim paper doesn't describe how should we identify our nodes. And the naive way would be just use IP port and an ID as an ID, but it's not good when you want to change IP and port without making other nodes think that old IP import and new IP port are 2 different nodes. So we identify nodes by UUID, and it not only allows you to change IP port without losing information in other member tables, but also it's consistent with Tarantul because Tarantul instances are also identified by UUID. And GC mode also really, I would say, strange moment. In original Swim, they say that if a Swim is declared dead, it should be deleted immediately from member tables. But it's not good if you want to catch a moment when this node is back on. So we made this behavior configurable to conform with the original Swim, and so as it could be really usable in production. You can turn off this thing. GC mode means garbage collection mode. You can access member table individually. You can add members manually, calling add member if you know UUID and IP port. You can remove member from member table manually. You can send broadcast message on a given port, or you can send the ping message manually calling probe member. Why would you need probe member if you have add member? The problem is that you don't know UUIDs in advance sometimes. For example, they could be generated after nodes are started. So when you don't know UUIDs, but you know IP port, you can send ping message. Ping message in Swim carries UUID of the sender, and ACK message also carries UUID of the sender. So with probe member, you can make 2 nodes exchange their UUIDs, and they will learn about each other, and then they will ping each other automatically. You can access individual nodes to take a look at member table size, or fetch individual member and look at its current status, its incarnation number, UID, IP port, and some other attributes we will look at them later, and iterate over member table calling pairs. Pairs is used in Lua language in 4 cycles. You can subscribe on events so as not to poll member table manually with some period. Your function will be just called immediately after any update. And your nodes can voluntarily quit cluster without killing them and make other nodes that this is dead. So other nodes will learn that this node has left the cluster voluntarily. It's method quit. Here is a short example how Swim works. I started 2 Swim nodes on different ports, subscribed on events on left node, and this subscription function just stores event in a global variable so as I could print it later in console. I link these nodes using probe member. Now they know about each other. I can see this in member table size. 2 means this node and some other node. Event was delivered, I printed, and I see member affected by this event, and exact event is new and is something else. There are many events. Is new incarnation we have, is new status. And after I drop one of these members, other member notices this, and I didn't do any manual pings. As we can see, its status is shown as dead. And now 2 extensions of Swim, which appear to be really useful, without which Swim was just impossible to use in production. First extension is anti-entropy, and each extension I will show as a problem which classical Swim doesn't solve, and the extension will be a solution. Here is an example. We have 2 nodes A and B. They know about each other, send ping messages, and node C is added. It knows only about B. For example, B could be an anchor node about which or every other node knows, and from which they hope to fetch the whole cluster topology. By classical Swim, B should now send an event to node A saying that, hey, there is a new node C, you can ping it as well. So as nodes A and C would know about each other. But this is UDP, so this message can be lost. And since events have limited lifetime, it just won't be sent ever again in classical Swim, and A and C will never see each other. This is solved by anti-entropy component. It's a third component of Swim, also independent from other components, and it's very simple. We just take random subset of sender's member table, and this allows to synchronize things which weren't disseminated by dissemination component. Here, B will always send this anti-entropy section where it will contain A and C, and no A and C will learn about each other eventually. Next extension is payload. The problem is that if we found a Swim instance on a given IP port, how will it learn what else works on this machine? Because we just know Swim port and we don't know anything else. On what port Tarantul works here or whatever uses the Swim. And we needed a way how to disseminate not just Swim events, but arbitrary data defined by application, and it's this payload. You can set your own data up to 1,200 bytes, which contains any information you want to send to other node. And it will be disseminated to the whole cluster just like any other piece of data, like incarnation, IP port, or what else Swim defines. Here in this example, I started 2 Swim nodes. On one of them, I started Tarantul on a given port and set payload of this instance as a port of Tarantul and some arbitrary second key. Set payload is a Lua interface, so you can set any Lua object as a payload. String, number, table, array, map, or raw data created from your C function or something. Now I connect them, this time using broadcast. It's just the same as probe member, but sends on all IPs using given port. And I can see this payload on another node. It was delivered, and I can use this delivered port to connect to remote Tarantul, and it works. Existence of payload makes it possible to send here not only IP ports, but also login, password, or any other credentials you want to send to access, for example, the same Tarantul. And it makes it impossible to use in open networks without encryption. So you could encrypt your payload by yourself, but other fields of SWIM would be not encrypted. And with encryption component, you can encrypt packet as a whole. Even UDP header is considered compromised, so it's duplicated in UDP packet body and is also encrypted. We have some algorithms which you can choose using setcodec method, mode of operation of these algorithms, and your private key, and all the packets will be encrypted inside transparently and decrypted on the receiver nodes. Next extension is restart detector. The problem is that incarnation sometimes is not sufficient. Its main problem is that it's not persistent. Let's consider an example. Two nodes, A and B. Node A has incarnation 1 and payload blue circle, and node B knows this information. Now A is turned off and back on, but with different payload. Incarnation is not persistent, so after restart it has the same incarnation but different payload, and when it tries to tell this to node B compares received incarnation and last known incarnation and just don't do anything because it thinks that it already knows everything about A. So incarnation just is not enough here, and it was fixed by splitting incarnation in two parts. Generation and incarnation. Generation is a persistent part of incarnation, and incarnation works exactly like in classical SWIM. And all the information first is checked by generation and then by incarnation values. Here is how it works. You can either set generation manually if you persisted by yourself in Tarantul or somewhere else, or you can leave it default and it will be current timestamp. Now I configure SWIM instance, create a second one, I connect them. I restart, for instance, with a newer generation, and I can see this as an event on another instance. So the problem of payload not being disseminated is solved, and also we have restart detector, here. And this event can be seen as is new generation. You can somehow use it in your application. Here is finally, we are ready to build a cluster, as it was said in the talk title. The formal description of task is this. We have n data centers, and in each data center we start two nodes and want to make each data center have one replication set with two nodes. I will write a script which will work on each instance, the same script. It takes 4 arguments, data center ID, SWIM IP port, Tarantul IP port, and the UID of this node. Now I write function which will be called each time when this node finds an event in the cluster. Here we will take a look at the event and check if the event is that a new node is discovered in our data center, then we add it to nodes table. Then I activate the subscription, configure SWIM, set this payload so with other nodes will know my data center and IP port of Tarantul. Then I start background fiber, which will try to find new nodes by periodic broadcasts, 1 per second. And I just wait until a second node in my data center is found. After this, I am ready to start Tarantul, calling box CFG with replication, and everything will work out of box from here. And we have built the cluster. There are other applications where SWIM can be really useful. First is monitoring. This is why gossip protocols were invented after all, and leader election algorithms, surprisingly, because in leader election algorithms, usually it's not only about election of a leader. Usually it's also about checking that the leader is still alive. So monitoring of the leader. And here, this component monitoring can be totally replaced by SWIM in theory. For example, in Raft, where leader is elected, it sends it's being monitored by other nodes, and we can replace this Raft component by Swim. How fast Swim is? For checking this, I created a program which simulates clusters of any given size in some virtual environment, and it was used for unit testing mainly, but appeared to be really useful for benchmarking as well. Here is a plot where how fast an event is disseminated depending on cluster size if each node sends pings and events once per second. Here we can see that on a cluster with 25 nodes, failure of one node was fully disseminated to all the other nodes for 4 seconds. 100 nodes for 6 seconds, 300 nodes for 7, 500 nodes for something about 7 and 8, and 800 for just 8 seconds. And let's compare with theoretical estimation with logarithm of 2, and we can see that it's very close. So Swim is just really fast, and it doesn't add overhead to your application because its implementation is very efficient in pure C, not in Lua, so there is no garbage collection or anything else which could waste time. So on the summary, what Swim can give you? It can give you detection of events in the cluster, or such as failures or any other arbitrary events, and dissemination of these events on the whole cluster. And it's very simple to understand, to use, to implement. It's available. Firstly, it's available as an open source project, so you can just go to GitHub and take a look at all the code commits and documentation. And in terms of application, it's available before Tarantul is configured, before application is started, so you can use it to start Tarantul as I did in the build cluster script. And it's already approbated in production systems and appeared to be very good, especially in conjunction with vShard module, Tarantul vShard. It's a horizontal scaling module for Tarantul, where monitoring is also a really important task as well. And what are the plans for further development of Swim as a protocol and as a part of Tarantul? First, as I said, it's really promising idea to replace some part of Raft by Swim. And we are going to try this. Swim can be used for cluster auto build and auto configuration, so you just start several Tarantuls, they discover each other and join into a replica set without any configuration. And there are some ideas about more extensions to Swim which could be added, especially against false positive failure detections. Thanks for your attention. No, we encrypt in user space, not on transport level.
Any more questions in the room?
On your graph of performance, was that measured with any network failures in it? Or like
Yeah, here it was possible to add some packet losses with a certain percent configurable.
What's the exact relationship between the Swim protocol in your implementation and the Tarantul? Are they independent of each other, or do they need each other?
Could we please repeat?
So you have the Swim implementation, and then there is Tarantul. Is it one thing, or are they sort of independent of each other?
They are independently, they are so independent that even in the code they are almost do not intersect. So, yeah.
Okay, thank you.
Thank you for the talk. Do any other projects use the SWIM protocol?
It's used in production systems. You mean out of Tarantul? Not?
Yeah, other than that, any additional?
Yeah, I listed some. Cassandra, Consul, ScyllaDB, Scuttlebutt.
I thought those were using more custom kind of gossip protocols. Are they using SWIM as a kind of?
Some of them use exactly Swim, but also with some extensions. For example, such thing as anti-entropy extension is implemented almost in every Swim, which proves that it's a necessary thing.
Okay, thanks very much for coming to talk to us.